Just- yeah. Yeah. No, that's true. I don't think it's a nickname. I think that's the actual name. Let's see here, lecture 29. Ah, thank you. So up till now, we've been, like last about 2 hours of lecture, so we've been studying maximal and prime ideals. And the main results are that if we take a ring, a commutative ring with identity, we mod by a maximal ideal, we get a field, right? And that's if and only if, right? If a quotient ring by an ideal is a field, that means that the thing you're quotienting by is maximal. And likewise, it's if and only if the quotient ring modding by an ideal is an integral domain, that means that that ideal is a prime ideal. And of course, since every field is also an integral domain, that means that a maximal ideal is automatically a prime ideal. However, on the other hand, not every integral domain is a field. Like the integers are an integral domain, but they're not a field because 2 does not have an inverse, multiplicative inverse, right? Half is not in the integers. So certainly there are prime ideals which are not maximal, right? And then, of course, we talked about Euclidean domain and principal ideal domain and unique factorization domain, and we saw the interplay between those. The main result, one of the main results of note is, of course, that if we have a field and we look at polynomials over the field, they in fact form a Euclidean domain, which implies then that they're a principal ideal domain, which then in turn implies that they're a unique factorization domain. So these are the kind of things you want to take away from the, you should write out the big theorems that we've done in the last lectures. Those are things you want to kind of take with you. And anyway, once we get a little bit closer to test 3, I will tell you guys the proofs of which ones I expect you to be able to do, So I already kind of indicated that with some foreboding comments here and there, but, I'll try to circle back, do that again. All right, so this brings us to the next thing, the next logical extension. Oh, I'm sorry. Extension fields. And so here's the definition. A field E is an extension field of F if F is a subset of E and the operations of F are those of E restricted to F. Right? We call F the base field of the extension. All right? So we already have a number of examples of this phenomena. All right? Let me draw your attention to a few of them. So the real numbers. Right? R is an extension of the rational numbers. Right? Rational numbers are a subset of real numbers, and they're with respect to the same arithmetic, right? I mean, the same multiplication and addition. So here, you could take Q as the base field and R as the extension field, all right? But you can do more than that, right? You can take the complex number system and notice that it is an extension of what? Well, that's true, but it's an extension of R, right? And you're right. Yeah, that was my example 3, actually, which was that C is an extension of Q. That's also true. So that, I mean, that's basically a very sort of obvious theorem, right? Here's a theorem. If, let's see here, if E extends F1 and F, oh, I can't do it. Just a second, I got to get my letters straight. I'm just trying to make this up, and whenever I do this, bad things will happen. Yeah, let me, yeah, I think you got it. Let me draw a picture. So we'll put E over F1 and F1 over F, right? So what I'm saying is that if E extends F1 and F1 extends E, then extends F. I'm an idiot. I can't keep my letters straight. Then E extends F. I mean, the proof of this is essentially just set theory, because what I'm saying is that, you know, you have two subset relations, right? Like F1 is a subset of E, right? And F1, good grief, I can't do anything.
F is, no, you got to take off the 1. And F is contained in F1.
Yes, F is a subset of F1. There we go. So if those two things are given, then what? F is a subset of F1 is a subset of E. And then, of course, the arithmetic is shared by, the arithmetic of E is shared by F1, and hence the same arithmetic is shared by F as well. So that makes E an extension of F. In this kind of situation, you could say, we call F1 an intermediate field. You know, between F and E, right? And this picture I just drew is sometimes called a tower of fields, right? So if I draw the tower of fields for example 1, it's like R is up here over Q, right? And example 3, I'll do it like this. So we've got complex numbers over the real numbers over the rational numbers, right? So this is the base field, the intermediate field. Anyway, so there's more though, right? There's things that are less familiar we've played with. So example 4, and I guess I don't think I ever gave you guys this as a homework problem. I really should have. If you look at Q, adjoin the square root of 2, in other words, A plus B root 2, you can prove that that's a field. So essentially the thing that, I mean, so what should I say here? I've before talked about this. You notice the square brackets? So what that is that's the ring. That's the ring which is formed by just adjoining the square root of 2. I mean, essentially it's exactly this set, right? The notation Q parentheses square root of 2 means smallest field containing Q and the square root of 2. You can prove that that ring is in fact that field. So it wasn't wrong to write the parentheses rather than the square brackets. The thing that I never made you do in homework that I should have is the following calculation. How do I know that this ring is already closed under inverses? So like what's a plus b root 2 inverse? Well, here's what it is. You just do a plus b root 2 in, I'll just write it this way. So you do this times, so it's what I've been teaching my intermediate algebra class this last week or two. Rationalize the denominator, and what do you get? Two b squared, right? When is the denominator 0? Yeah, when a squared minus 2b squared equals to 0 has what solution?
B equal to 4, no, sorry.
Mm-hmm.
For rational numbers.
Yeah, it looks like we'd have to have a over b equals to plus or minus the square root of 2, right?
Yeah.
And that's impossible with rational numbers, which is good news because that means that my alleged formula, that proves that this is in fact an element of Q adjoin square root of 2 as a ring, right? But also you can prove that that is the multiplicative inverse of a plus b root 2. You can, simple exercise, you can show that a minus b root 2 over a squared minus 2b squared, that times a plus b root 2 is equal to 1. So what I've shown then is that an arbitrary non-zero element of this ring has a multiplicative inverse. Therefore, a square brackets, Q square brackets root 2 is in fact a field already. So because we already knew it was a commutative ring with identity from previous things we've done, and notice that Q is a subset of this, right? Agree? And square root of 2 is an element of it, isn't it? Agree? So take b equals to 0, you can get an arbitrary rational number. Right? Take a equals to 0, put b equals to 1, you got root 2 in it. It has both of these things. So, and you can't make it any smaller because of our work before on the prime subfield, right? If we have characteristic 0, then the prime subfield has to be contained, right? And the prime subfield is Q here. So you can't get smaller than Q, and you can't get rid of root 2s. This has to be the smallest field. Anyway, so all of this to say Q square bracket root 2 is equal to Q parentheses root 2. But notice there is a difference in that notation, and it's intentional. All right? Like, to give you another example of this notation, this is polynomials. Right? This is polynomials. What's this?
That's R of X. I don't know. This is as a function.
So x is an indeterminate here, right? So this is the smallest field, which contains both the real numbers and the indeterminate x, but also its inverse. So a natural way to think about this is actually rational functions, or rational expressions. In other words, things of the form f of x over g of x, where f of x, g of x are polynomials over the reals. do rational functions have inverses? Think about it. Like if I want it, what's the inverse? If this is non-zero, what's the multiplicative inverse of f of x over g of x? G of x over f of x, right. So any rational expression has a multiplicative inverse, and certainly it has x in there, and it has 1 over x in there. And you can prove that that's the smallest such thing. It's also, I want to say it's also what you get from doing the field of fractions construction that we did. If you do the field of fractions over polynomials, what you get is r parentheses x. Anyway. So I also give an example in the notes. If we take z2 of x mod x squared plus x plus 1, right? This is a, let me call this E. It's a, this is an extension of z2, right? We proved that that was a field, right? Because x squared plus x plus 1 was irreducible, hence the ideal generated by x squared plus x plus 1 is maximal. And so that quotient is a field. And it's a field which naturally takes, it's a field which takes z2 as a subset, right? Let me just talk a little bit more about notation here because, so if we want to, we could say E is what? It's things of the form what? Let's see, so it's like A plus BX plus, this ideal. That's what things in this look like, right? But another notation for this, like I introduced last time, would just be to let alpha equal to, x plus the ideal, x squared plus x plus 1, right? So with that notation, this is just what? This is A plus B alpha. A and B are in Z2, right? So with respect to this notation, so here's where the definition lets us down a little bit. To be fussy, is Z2 a subset of E? Strictly speaking, is Z2 a subset of E? It depends on how we construct Z2, right? There's a set of cosets which is exactly isomorphic to Z2. So really when we say that it's a subset, we're allowing ourselves the possibility that there's a isomorphic subset of the extension field, which we count that. All right, so that you have to understand this subset condition in view of our understanding that isomorphic fields are the same field. So now I'm getting fussy. Like, are the complex numbers 2 by 2 matrices of a particular form? Yeah. Is it A, B minus BA? Or are complex numbers R of x mod the ideal generated by x squared plus 1, which would mean they're equivalence classes of polynomials? Are complex numbers pairs of real numbers subject to a particular multiplication in the plane, the so-called Gauss's construction, or maybe Argand? See, depending on what you come down as, the construction of complex numbers will inform whether or not you agree that real numbers are literally a subset of complex numbers or not. Like, actually, none of those constructions have the real number system as just a straight subset of those constructions. But there is a subset of each one of those constructions which is isomorphic to the real numbers in the sense of a ring isomorphism. And so we count that as being a subset. And we say that R is an extension. C is an extension of R. So I wanted to warn you about that, because if you become aware of this issue and you dogmatically think that this subset actually literally means subset, it may or may not, depending on how you view the construction of f to be. The point is there has to be a field which is isomorphic to f, which is a subset of E. Right? There has to be a subfield of E which is isomorphic to f. That's what we really mean. But anyway, people don't want to say that in the original definition because they want to make things seem simpler than they are. But here, certainly, this is exactly Z2 adjoined by alpha, where alpha squared plus alpha plus 1 equals to 0, right? So what we're doing, this extension field E, is you're taking Z2 and you're adjoining an element E, alpha rather, such that alpha squared plus alpha plus 1 is equal to 0. That there is no such number already in Z2. 0 doesn't work. 1 doesn't work. 0 squared plus 0 plus 1 is 1. 1 squared plus 1 plus 1 is 1 in Z2. So this is new. All right, alpha is something new. A stupid example is like what happens when what if you take the real numbers and you adjoin pi? So what's the smallest field which contains the real numbers and also pi? Well, the real numbers can include pi already, so this is just reals again, right? Or if you take the rational numbers, right, and you adjoin a half, guess what? Still the rational numbers, right? If you adjoin an element to the field that's already there, the extension, the smallest field which contains that real number and that adjoined element, just the field again. So adjoining elements is most interesting when you're adjoining something that's not already there. All right? That brings us to the fundamental theorem of field theory, which apparently is due to Kronecker in 1887. Yeah, the same of Kronecker delta fame. Although I would guess that was not particularly, people make a big to-do about that kind of thing, but it's doubtful he actually thought that was a big deal. Although I will say, like the Kronecker delta notation.
Essentially, like either something's 1 or minus 1 depending on.
A 1 or 0.
Yeah, 1 or 0, just depending on like how you choose I and J for a particular.
Right. It's this thing.
Set.
Kronecker delta ij 1 if I is equal to j, 0 if I is not equal to j.
Basically, just kill sums.
Yeah.
It's a sum killer. Does anything come from that? Yeah, there's a lot of use of that Kronecker delta.
It's the components of the identity matrix in linear algebra. It's the formula you need for like the dot product.
You know how in a matrix all the diagonals are 1. That's the identity matrix. That's because that's the A11. IJ's IJ equals each other 1. IJ equals straight down.
Oh.
That's where that.
Who put the floor so far down there?
But you guys have never seen it written like. Nah, I didn't get it until differential geometry. I didn't see that notation until differential geometry. Yeah.
You won't see it unless you talk to somebody like me. Fundamental theorem of field theory. All right, so here it is. Let F be a field. All right. And f of x, a polynomial over that field, non-constant. All right. Then there exists an extension field E of f, all right, in which f of x has a 0. So here's the proof. So we'll let f be a field. And f of x, a polynomial with a degree greater than or equal to 1, which is me saying it is non-constant, right? It's not a constant polynomial. All right. Then, since, f of x is a unique factorization domain, right? There exists a factorization of f of x into irreducibles, right? P of x times other things, whatever. I'll call it g of x. So, I mean, of course, like, it doesn't so much concern me what the other stuff is in the factorization for the purpose of this proof, all right? But the remaining things could also be irreducible factors. They might be a number. It just depends on the details of the polynomial, right? The point is you can factor any polynomial into a product of irreducible polynomials and, like a constant out front or something. All right. So then what? Observe if P of alpha equals to 0, then f of alpha equal to P of alpha, G of alpha is equal to 0 as well, right? So it suffices to prove that P of alpha is equal to 0 for some alpha, right? Agree? There exists alpha in E such that, phi sub alpha of P of x, which is equal to P of alpha, right, is equal to 0. And that's the evaluation homomorphism. Right here, that's the evaluation homomorphism from the extension field that we're about to construct. All right. So, all right. Let's let P of x, here's the details for P of x. P of x is equal to, an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a sub 0. All right? Then if we let E equal to polynomials in F, right, mod the ideal generated by P of x, well, P of x is irreducible, therefore that's a maximal ideal. Consequently, this is a field. Since P of x is irreducible, implies that the ideal generated by P of x is maximal, implies that the quotient by a maximal ideal, of course, as we were talking about at the start of class today, is field, right? So that's a field. All right. So then, as I've been advertising for some examples, let's let alpha equal to x plus the ideal generated by P of x, right? Notice if we take alpha to the, jth power, we likewise get x to the jth power plus the ideal generated by p of x. It's easy enough to prove this for like j equals to 2. If you multiply the x plus the ideal by itself, you get x squared plus the ideal. So, and then you could do induction to prove it for like, for j and the natural numbers. All right. So what's p of alpha? P of alpha means what? That means that we put alpha in the place of x, right? So this is an alpha to the n plus an minus 1 alpha to the n minus 1 plus plus a1 alpha plus a0, right? But what does that actually mean? That means, going back to the x notation, that's an x to the n plus the ideal generated by p of x, right? Plus an minus 1 x to the n minus 1 plus the ideal generated by p of x, right? Plus a1 x plus the ideal generated by p of x. I'm getting really tired of writing that. Plus, finally, a0 plus the ideal generated by p of x. All right, so how do we add cosets? We add representatives, right? So this is literally an x to the n plus an minus 1 x to the n minus 1 a1x plus a0 plus the ideal generated by p of x. Please tell me I have not been on the other board. Oh, phew. What is this?
Polynomial.
What is that polynomial?
It's
Is
added, but it's added with a prime, where p of x is irreducible.
p of x is irreducible, that's true. So look here, right?
2px.
It is p. This is literally p of x plus the right. So by the arithmetic of cosets, that's just the ideal generated by p of x, right? In other words, that's 0 in E, which is, again, f of x mod p of x, right? The factor ring where you're quotienting by the ideal generated by p of x, that is the ring in which the ideal generated by p of x functions as the 0. This is what we want. See, we have p of alpha is 0. So I have a question. Does F need to be a field? I guess my
Does f need to be a field?
right. If F wasn't a field, could you still do this? What if F was just a integral domain?
Well, if it's a UFD, you can still do it.
Or yeah, what if it's a UFD? Yeah, we do. You're right. Well, goodness, do we even need that? See, I don't think we even need that. I think that actually there's a version of this theorem that you could still write if you just had a commutative ring with identity. What I'm saying is, and here's the theorem, And this is not a theorem of field theory because it's not about fields. But if R is, let's say, commutative ring, and f of x is a polynomial over that ring, then there exists, let's say, I don't know what you want to call it. I'll call it R tilde for the lack of imagination. There exists R tilde such that alpha, an element of R tilde, has f of alpha equal to 0. And here, R tilde is, again, a commutative ring. Now maybe I'm maybe I'm missing something, but if you guys can poke a hole in it, go feel free. But so essentially, my point here is, if we were to take the polynomials in x and just mod by the ideal generated by f of x, can I do that? Is that something I can do over? Well, if it's a commutative ring with identity, right? What do I know about? I don't know much about R of x. R of x doesn't even have to be an integral domain, right? Zero divisors in R lead to zero divisors in polynomials over R. But that doesn't really stop me from, maybe, I'm trying to remember, what was our construction of, see, I keep forgetting, what was our starting point for building a factor ring? I think we just had commutative ring, right? The issue was we need to mod by an ideal. That's non-negotiable. We have to mod by an ideal. But I'm pretty sure that this is still an ideal, right? I mean, you can try it. Right. So I think you can prove that that's an ideal. It's closed under subtraction, and it's got the uber closure. So that's still an ideal. So this is a well-defined factor ring, right? And if you call this thing R tilde, essentially the same calculation gives what? F of alpha equals to 0 for alpha equal to what? X plus the ideal generated by f of x. So why do we assume that f is a field, and why do we assume that, why do we do what we do in the fundamental theorem of field theory? It's the fundamental theorem of field theory, right? It's a theorem about fields. The theorem I just wrote is a theorem about something else, right? It's a more stripped down version of this field theory theorem. But this is what I need in the research, Audric. See, because our commutative ring would be like an algebra.
Yeah.
And so what this is saying, you can take polynomials over the algebra and mod by the polynomial, and you'll still get, well, you don't get a field, but you get an extension of the algebra,
Yeah.
which is, again, an algebra of the same type, but it has a new element,
Yeah.
perhaps, that, does our bidding in a particular way. This is the necessary ingredient for the stupid solution. This is how I build the A prime we talked about. But it's really it is just this argument. It's just this argument gives you fields because you're assuming, well, you've got a field, so you've got a unique factorization domain, which means you can find an irreducible factor. And if you can find the irreducible factor, that means you can mod by a quotient by a maximal ideal. If you can quotient by a maximal ideal, you can make the factor ring be a field, and then that field naturally extends F, where you identify F with the cosets which take constant polynomials as their representatives. Yeah. So, just to give you, you'll forgive me here for a moment, I'm misbehaving a bit. So hyperbolic numbers. What example is this? 7. So hyperbolic numbers are kind of weird things. They are something of the form a plus bj, such that a and b are real numbers, and j squared is equal to 1. All right. Here, j is not a real number. It is something else. In the same way that the imaginary number is not a real number, j is not a real number. So this is the hyperbolic numbers. And, you know, you could do things like, you could adjoin imaginary units to the hyperbolic numbers by doing this. You could just basically take polynomials in, let's say, in x, and mod by the ideal generated by x squared plus 1. By the way, you can prove that there does not exist a polynomial with hyperbolic number coefficients which takes I as its which takes a hyperbolic number whose square is minus 1. Like, there is no quote-unquote I in the hyperbolic numbers. But there is an I in this. See this? And so, you know what Nathan did in his work, you read his papers and stuff, instead of using x, he just uses like k. And so he just goes straight to putting the one thing he's going to use, and he just basically says, well, that's h with k adjoined, if you will. And so that's something like a plus bj plus k times c plus dj. It works out to that. So, for what it's worth, and I have not defined these things in here, mind you. You know, H is a real algebra of dimension 2, whereas this thing is a real algebra of dimension 4. And I'm talking about dimension in the sense of vector space dimension. But I have not defined algebra in here, by the way. So this is a funny thing, actually, if you stop and think about it. In all of your course in abstract modern algebra, did you ever define algebra? You didn't, right? But the word algebra can be given, you know, specific technical meanings. So, for example, an associative algebra with identity is a vector space paired with a multiplication, a binary operation, which is associative, and so it satisfies certain distributive properties with respect to the multiplication, and often I usually assume it's unitable, so it also has a multiplicative identity. So actually an algebra would be, it's a commutative ring, but it's more than that because it's also a vector space, right? Most of our commutative rings we've looked at in this course, they haven't also been vector spaces. Some of them, yes, but not all. Anyway, I digress. My point, I just wanted to mention that this idea doesn't stop at field theory. This idea of quotienting by what you want to have 0, you know, just take polynomials over the object and then quotient by the polynomial, which being 0 describes the element you're trying to adjoin. This is a general trick, much more general than fields. All right. So, go on here. Example 8. Here I look at f of x equal to x squared plus 4x plus 5, a real polynomial, right? And notice f of x is x plus 2 quantity squared plus 1, right? So there does not exist c in the reals such that what? F of c equals to 0. But if we want, we can extend the reals, right? We can look at the extension field E to be R of x mod this irreducible, well, I don't know what I just said, but it wasn't right. This irreducible polynomial, x squared plus 4x plus 5, right? And we can write that in the form what? A plus b alpha, right? A and b are real numbers, and alpha equal to x plus, f of x. And of course, by construction, alpha squared plus 4 alpha plus 5 is equal to 0. So what is this field? See, that becomes an interesting question to start asking. We've constructed some new field. Do we know what it is? Like up to isomorphism. What is it isomorphic to? What do you guys think? This one. See, another way I could have written this would have been alpha plus 2 squared, right, is equal to minus 1. So to me, that suggests we might use the notation I equals to alpha plus 2. And see, if I do that, then A plus B alpha, I should really look at as A plus what? Alpha is I minus 2, right? So, of course, that's what? That's A minus 2B plus BI. So my intuition here is this is just an ugly notation for complex numbers. It's just an awkward presentation of the complex numbers. The isomorphism I would suggest we could write, and you can prove it's an isomorphism, is that psi of A plus B alpha is equal to A minus 2B plus BI. And I believe you could prove that that mapping from E to the complex numbers is an isomorphism of fields. If you wanted to, I could spend the next 20 minutes working out the details of that, well, 10 minutes, but I'll just do a little bit. Does 1 map to 1? Yeah, psi of, right. Well, I'm claiming it, but just because I say it's an isomorphism, at the moment there's a giant stinking question mark there, yeah? So psi of, what is 1? Yeah, 1 plus 0 alpha, right? So 1 plus 0 times alpha, if you want to write it that way, it maps to 1 minus 2 times 0 plus 0 times I, right? Also known as 1. So 1 maps to 1, that's a start. You can easily check that this mapping is linear. Like if you replace A with you take A1 plus B1 alpha plus A2 plus B2 alpha, then you'll get A and B appear linearly here, so you'll be able to prove that psi of a sum is the sum of the psis. What's perhaps more interesting, and maybe I should actually take a look at, just to make sure I'm not just lying to you, is does it preserve multiplication? That's actually kind of non-trivial. Let's see if we can work that out. So is psi of A plus B alpha times C plus D alpha, what's it equal to? Well, that's psi of, how do these multiply?
DC,
Mm-hmm.
AD alpha,
Yeah, AD plus BC
BC
alpha.
BD alpha squared.
Yeah. And how does that go? What's alpha squared equal to? Alpha squared is equal to 4 alpha minus 5. Actually, it's minus 4 alpha minus 5, right? See, because alpha squared is minus 4 alpha minus 5, right? So that's how that goes. And so, all right, so what do I got? I've got psi of AC minus 5 times BD, right? Plus parentheses AD plus BC minus 4BD times alpha. See, that's what I need in order to use my formula for the isomorphism, right? So I'm going to go back to my formula for the isomorphism and decorate it a little bit. I'm going to put some bars over the A and B so you can better understand what I'm doing. What I'm saying is that this right here is A bar, and this right here is B bar, not to be confused with the fictional elephant Babar, something else entirely. Let's see here. I never could get into that cartoon. It just seems kind of boring. A bar, B bar. Yeah. So we do, by definition, this is what? A bar minus 2B bar, right? Plus B bar I. And that's AC minus 5BD minus twice AD plus BC minus 4BD, excuse me, plus parentheses AD plus BC minus 4BD I. We will refer to this as exhibit star. Okay? Because I'm definitely not going to try to go in one foul swooping calculation to prove that it's multiplicative. I'm going to go on the other side. And now I'm going to calculate psi of A plus B alpha times psi of C plus D alpha. And I hope I get the same thing. This is much easier. See, because all I have to do here is A minus 2B plus BI times C minus 2D plus DI. So that's a trinomial times a trinomial. There are 9 terms. Here they are. AC minus 2 DA plus ADI minus 2BC plus 4BD minus 2 BDI plus BIC minus 2 BDI. And then plus BDI squared. All right, so I'll collect all the real stuff. I got myself an AC. How many BDs do I got? I got myself a 4BD right here. got myself a minus BD there, so I got plus 3 BD. And let's see here, how many ADs am I looking at? I've got myself minus 2 AD. That's this guy. Anything else real? I'll keep it red again. Minus 2 BC. Mm-hmm. Okay. I think that's it for the real stuff. And then for I, I've got AD. I've got a BC plus BC. And then I've got minus 2 BDI, which is minus 4 BD. I factored my I out. Hey, what do you know? I think these match. At least the imaginary part match, right? If we compare star and star star. So let's see here. I got my AC term. Now I claim 3 BD, right? So I got minus 5 here, but notice that I also have plus 8 BD over there. Minus 5 plus 8, 3. Then I got my minus 2 AD. Here's my minus 2 AD. Where are my minus 2 BCs at? Right here. And then that's it. And the imaginary, it matches. Hooray. Now, this illustrates my method. If I'm trying to prove two objects are isomorphic, what I try to do is I try to find something that is sort of encapsulates what they are, and I try to map that thing. So in my view, the imaginary number I is what makes the complex numbers what they are. So if I can understand what is playing the role of the imaginary number and the thing that I think is imaginary numbers with bad notation, then that's what I'm gonna call I. And if I do that, then that will suggest the isomorphism. That's what I did here. So this is actually a general technique for finding isomorphisms, is try to come to terms with, because in some sense what an isomorphism is a change of notation. So if you can come to an understanding of what it is you're looking at, that'll do you well. All right, so my next example oh, I really hope that yeah, okay, we're good. We're good. Whew. All right. So I will try to spare you some of the details of this next example. I'll try to be brief on this one here. So here, what example am I on? 9? I'll go with 9. I like it. So here I have f of x equal x to the 4th minus 5x squared plus 6, which is, by the way, x squared minus 3 times x squared minus 2. All right? And I'm looking at this as a polynomial with rational coefficients. All right? So here, f of x is reducible, right?